Somewhere in the constellation Ursa Major, roughly 30,000 light-years from where you are now, there is a gathering of ancient stars so small and so faint that astronomers cannot agree on what it is. It contains approximately 60 stars. Its total mass is roughly 16 times the mass of our Sun. Its light output is only 11 times the brightness of a single star like ours. And yet, this whisper of matter might be a galaxy, not a miniature version of the Milky Way. Something stranger. Something that challenges the very definition of what a galaxy is. What you are about to hear is the story of the smallest, faintest object ever found that might still deserve to be called a galaxy, and why that word might be breaking. If you enjoy deep journeys into the strangest corners of the universe, I would really appreciate it if you could hit that like button and subscribe. Now, settle in, get yourself comfortable, let's begin. When you hear the word galaxy, a specific image forms in your mind. You see a vast spiral of light, hundreds of billions of stars turning slowly through space, arms trailing luminous dust, and newborn stellar furnaces across distances so immense that light itself needs 100,000 years to cross from one edge to the other. You picture the Milky Way, our home, with its roughly 400 billion stars burning hydrogen into helium, in a disk so wide that every civilization in human history could rise and fall 1,000 times before a single photon completes the crossing. Or you picture Andromeda, our nearest large neighbour, 1 trillion stars strong, its faint glow visible to the naked eye, from 2.5 million light-years away. These images are correct. They are also incomplete in a way that matters enormously for what comes next. They are incomplete because they establish an expectation. Galaxy means big. Galaxy means luminous. Galaxy means an island universe, a self-contained metropolis of stars massive enough to shape the curvature of space and time around it. The ancient Greeks called the Milky Way galaxias, from their word for milk, because the band of light stretching across the sky resembled spilled milk against the darkness. When Edwin Hubble proved in the 1920s that the so-called spiral nebulae were actually distant collections of stars lying far beyond the Milky Way, the word galaxy expanded to describe all of them. From that moment, galaxy became synonymous with immensity. But the universe does not care about human vocabulary. It does not adjust its structures to fit neatly inside the categories we invent. And over the past 2 decades, astronomers have discovered objects so small, so faint, and so ghostly that the word galaxy begins to crack under the pressure of what it is being asked to describe. The trouble started in 2005. That year, astronomers mining data from the Sloan Digital Sky Survey, an ambitious project that mapped millions of stars across a large fraction of the sky, found something strange. Embedded in the data were faint smudges of stars hovering around the Milky Way. These were not bright satellite galaxies like the Large Magellanic Cloud, visible to the naked eye from the southern hemisphere and home to 30 billion stars. They were something far more subtle. Tiny overdensities of stars, barely detectable even with sophisticated matched filter algorithms, designed to pick out faint stellar groupings against the crowded foreground of the Milky Way's own disk. Without the algorithms, a human eye scrolling through sky images would never have noticed them. They were hiding in the noise. Before these new discoveries, the known population of Milky Way satellite galaxies consisted of classical dwarf spheroidals like Ursa Minor, Draco, and Carina systems that had been catalogued for decades, each containing a few million stars. But the objects emerging from the Sloan survey data were something different entirely. They were fainter by factors of 100 or 1,000. Some contained only a few thousand stars. Others appeared to hold only a few hundred. Their total luminosities were less than the output of a single bright red giant star. If you placed one of these objects at the distance of Andromeda, no telescope on Earth could detect it. Astronomers called them ultra-faint dwarf galaxies, and they represented a class of object that no one had predicted would exist in such extreme form. The first question was immediate and obvious. Were these objects actually galaxies at all? A few thousand stars clumped together in space could easily be a star cluster. Globular clusters, the dense ancient balls of stars that orbit the Milky Way by the hundreds, typically contain between 100,000 and 1,000,000 stars, but the smallest known globular clusters contain only a few thousand. At first glance, these ultra-faint detections looked as though they could be stripped-down remnants of old star clusters rather than independent galaxies. They were the right size for clusters. They were the right luminosity for clusters. They looked, by every surface-level measure, like clusters. The answer came from a measurement that would become the single most important diagnostic in every classification dispute that followed: velocity dispersion. Velocity dispersion is the spread of speeds among the stars within a system, how fast the individual members are moving relative to each other, not how fast the system as a whole travels through space, but how vigorously the internal members are jostling around within their shared gravitational well. In a star cluster, the stars are held together by their own collective gravity. The total gravitational pull comes from the combined mass of all the visible stars. Measure how fast those stars move, apply Newton's laws, and you can calculate the total mass required to keep them bound. If the calculated mass matches the visible stellar mass, the system is self-gravitating. It holds itself together through the gravity of the stars you can see. No mystery required. No invisible scaffolding needed. But in the ultra-faint dwarfs, the speeds did not match, not even close. Stars inside these tiny systems were moving far too fast for their visible mass. The velocities implied total gravitational masses hundreds or even thousands of times greater than what the visible stars could account for. A system with a few thousand solar masses of visible stars was moving as though it sat inside a gravitational well belonging to something containing millions of solar masses. Something invisible and enormously heavy was gripping those stars, preventing them from escaping into the void. That something was dark matter. Dark matter makes up roughly 85% of all matter in the universe. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way that any instrument has ever been able to detect. It reveals itself only through gravity, through its pull on visible matter, and its bending of light passing nearby. Every large galaxy in the universe sits inside a vast halo of dark matter, extending far beyond the visible stars. In the Milky Way, the dark matter halo is estimated to contain roughly 10 times more mass than all the stars, gas, and dust combined. It extends outward for hundreds of thousands of light years beyond the edge of the visible disk. Dark matter provides the gravitational skeleton on which the visible galaxy is built. Without it, the Milky Way's outer stars would fly off into intergalactic space. Their orbital speeds are too high for the visible mass to hold them. Dark matter keeps the architecture intact. In the ultra-faint dwarfs, dark matter does not merely contribute to the gravitational budget, it dominates it almost entirely. These systems are not galaxies in the way most people imagine. They are not grand spirals. They are not luminous ellipticals. They are tiny clusters of ancient stars embedded inside dark matter halos, so massive relative to their visible content that the stars themselves become almost an afterthought. The visible matter is a rounding error. The dark matter is the structure. The galaxy, in a meaningful gravitational sense, is the halo. The stars are just tracers, luminous breadcrumbs marking the center of something overwhelmingly invisible. This realization forced astronomers to confront a question that had never seemed urgent before. What, exactly, is a galaxy? The answer had always felt intuitive. A galaxy is a large, self-contained collection of stars. But intuition collapses when you are staring at a system containing fewer stars than a modest open cluster in the Milky Way's disk, yet embedded inside a dark matter halo that outweighs all its visible stars by a factor of thousands. In 2012, astronomers Beth Willman and Jay Strader proposed a definition crafted to handle exactly this problem. They wrote that a galaxy is a gravitationally bound collection of stars whose properties cannot be explained by a combination of baryons and Newton's laws of gravity. In plainer terms, if you measure how the stars inside a system are moving, and the motions require more mass than the visible stars can provide, the system contains something beyond ordinary matter. It is a galaxy. If the motions can be fully explained by the stars alone, with no invisible excess, the system is a star cluster. Within the standard cosmological framework lambda cold dark matter, this definition reduces to a single diagnostic question. Does the object sit inside its own dark matter halo? If yes, it is a galaxy. If no, it is a star cluster. Dark matter becomes the dividing line. Not the number of stars, not the physical size, not the luminosity, not the shape or the color or the distance from the Milky Way. The presence or absence of a dark matter halo is what separates the smallest galaxy from the largest star cluster. Two objects could contain identical numbers of stars, occupy identical volumes of space, and look indistinguishable in any photograph. But if one sits inside a dark matter halo and the other does not, one is a galaxy and the other is not. This definition is elegant. It is also extraordinarily difficult to apply in practice. Measuring velocity dispersion requires obtaining spectra of individual stars within the system and determining their radial velocities, how fast each star moves toward or away from us, to a precision of better than 1 or 2 kilometers per second. For ultra-faint dwarfs containing only a few dozen stars bright enough for spectroscopy, the entire measurement depends on a small handful of data points. Binary stars, pairs orbiting each other, can contaminate individual velocity measurements and inflate the calculated dispersion of the entire system. Remove one such contaminant from a sample of only a dozen stars, and the calculated total mass can drop by a factor of 10. The difference between galaxy and star cluster can hinge on whether a single anomalous velocity reflects a dark matter halo or an undetected binary orbit that has nothing to do with the system's gravitational potential. There is a second diagnostic tool, less direct but sometimes equally revealing: metallicity spread. Metallicity, in astronomical usage, refers to the abundance of elements heavier than helium in a star's atmosphere. The very first stars in the universe formed from nearly pure hydrogen and helium left over from the Big Bang. No heavier elements existed yet. When those massive early stars died in supernova explosions, they forged and scattered heavy elements: carbon, oxygen, silicon, iron, and dozens of others into the surrounding gas. The next generation of stars formed from that enriched gas, incorporating heavier elements into their composition. Each successive generation became progressively richer in metals. This process is called chemical enrichment, and it operates as a one-way ratchet. Galaxies grow more metal-rich over time as stellar generations build upon the chemical legacy of their predecessors. A star cluster forms in a single burst. All its stars are born from the same cloud of gas at roughly the same time, and they share approximately the same chemical composition. The metallicity spread within a typical globular cluster is extremely small, often less than 0.1 in the iron-to-hydrogen ratio. All the stars were made from the same raw material, in the same place, at the same moment. There was no second generation, no enrichment from internal supernovae that stayed within the system. The debris from dying stars simply escaped the cluster's shallow gravitational well and dispersed into the surrounding galaxy. A galaxy, by contrast, retains the debris from its own supernovae. Its gravitational potential well is deep enough, thanks to dark matter, to hold onto the gas enriched by exploding stars. New stars form from that enriched gas, and their compositions differ measurably from the first generation. Over time, the galaxy accumulates a spread of metallicities across its stellar population. The oldest stars are extremely metal-poor. Later stars are progressively more metal-rich. This range of chemical compositions acts as a fingerprint, revealing that the system captured its own supernova products and formed stars across multiple episodes. The metallicity spread is indirect evidence for a deep potential well, and therefore indirect evidence for dark matter. So astronomers carry two primary tools for distinguishing a galaxy from a star cluster at the faintest extremes. Velocity dispersion reveals the total gravitational mass and whether dark matter is present. Metallicity spread reveals whether the system retained enriched gas across multiple generations of star formation, and therefore, whether its potential well was deep enough to hold on to supernova ejecta. When both measurements clearly indicate dark matter and chemical self-enrichment, the classification is secure. The object is a galaxy. When both measurements clearly show no excess mass and no chemical spread, the object is a star cluster. The trouble arises when the measurements are ambiguous, when the velocity dispersion is marginally resolved but could be inflated by binaries, when the metallicity spread is small but not quite zero, or when too few stars have been measured to draw a confident conclusion, when the system is so faint that only a handful of stars can be observed spectroscopically, and every single data point carries enormous uncertainty. At these extremes, the clean boundary between galaxy and star cluster begins to dissolve into a grey zone that unsettles everyone who works in this field. Before Ursa Major III Unions 1 entered the picture, the most extreme object pushing against this boundary was Segway 1. Segway 1 was discovered in 2007 in the Sloan Digital Sky Survey data, lurking in the constellation Leo, roughly 75,000 light-years from the Sun. It was initially considered a possible globular cluster because of its small half-light radius, roughly 30 parsecs, or about 100 light-years. Its total luminosity was staggeringly low, with an absolute magnitude of roughly negative 1.5. It was tens of millions of times less luminous than the Milky Way. If you gathered all the light from every star in Segway 1 and focused it into a single beam, it would barely outshine a few hundred suns. But spectroscopy told a very different story. Marla Gihar at Yale and Josh Simon at the California Institute of Technology measured the radial velocities of 24 member stars using the Keck 2 telescope and found a velocity dispersion of approximately 4.3 kilometers per second. For a system containing roughly 1,000 solar masses of visible stars, this was drastically too high. The implied mass-to-light ratio ranged between approximately 1,300 and 3,400, meaning the system was overwhelmingly dominated by dark matter. Segway 1 appeared to contain nearly 1,000 times more invisible mass than visible mass. Its stars were mere sparks drifting through the center of an enormous dark matter structure they could never reveal on their own. Chemical measurements reinforced the galaxy classification. Segway 1 stars displayed a wide range of metallicities, with iron-to-hydrogen ratios spanning more than 2 orders of magnitude. Some stars ranked among the most metal-poor ever found anywhere in the universe, with compositions barely enriched beyond the primordial hydrogen and helium of the Big Bang. Others carried significantly more heavy elements. This spread implied that Segway 1 had retained supernova ejecta across multiple episodes of star formation, behavior characteristic of a system with a deep dark matter potential well. A star cluster, with its shallow gravity, could not have held onto that enriched gas. It would have blown away with the first supernova. On the strength of both kinematic and chemical evidence, Segway 1 was classified as the least luminous galaxy known. It became a cornerstone of dark matter research on small scales. Its extreme mass-to-light ratio made it a prime target for indirect dark matter detection experiments, which used gamma-ray telescopes to search for signals from dark matter particle annihilation at the center of its dense halo. No signal was found, but the constraints were valuable. Segway 1 was pushing the limits of what astrophysics could learn from a handful of ancient stars. But even Segway 1 prompted debate. Some researchers questioned whether tidal interactions with the Milky Way had distorted its velocity structure. Others raised concerns about foreground contamination. Milky Way stars at similar velocities and similar positions on the sky could masquerade as Segway 1 members, skewing the dispersion measurement. The classification held, but not without persistent dissent. Segway 1 taught the community a difficult lesson. At these faint extremes, every measurement is fragile, every data point is precious, and every classification is provisional until confirmed by independent methods. Other ultra-faint dwarfs followed in the years after. Boots 1, discovered in 2006, sits roughly 200,000 light-years away, with a total luminosity of roughly 30,000 suns. Though far brighter than the most extreme ultra-faint dwarfs, its velocity, dispersion, and metallicity spread both support a galaxy classification, and its elongated shape hints at ongoing tidal disruption. Willman 1, also found through the Sloan survey, remained stubbornly ambiguous for years. Its velocity measurements were plagued by foreground contamination so severe that different analyses studying the same data reached opposite conclusions about whether it contained dark matter at all. The uncertainty surrounding Willman 1 was not an anomaly, but a warning sign. At these faint luminosities, every diagnostic tool that works cleanly for brighter systems begins to degrade, and the confident separation of galaxy from star cluster starts to slip. Each ultra-faint dwarf galaxy discovered forced astronomers to ask the same uncomfortable question: how small can a galaxy get? Is there a flaw, a minimum number of stars, a minimum luminosity, a minimum dark matter halo mass below which the concept of a galaxy simply stops making physical sense. Theoretical models within the lambda cold dark matter framework predict that such a flaw should exist. Below a certain halo mass, roughly between 100 million and 1 billion solar masses depending on the assumptions, the gravitational potential well becomes too shallow to accumulate gas, cool it, and compress it into stars. Conditions in the early universe, particularly the intense radiation that accompanied the epoch of reionization, permanently cut off the gas supply to the smallest halos, ensuring that only those halos massive enough to have collected gas beforehand could ever form stars. Below this critical threshold, dark matter halos exist in abundance, predicted by the millions around every Milky Way-sized galaxy, but they remain permanently dark. No stars, no light, no visible trace at all, just invisible clumps of dark matter drifting silently through the halo. How many of these dark halos exist remains one of the most contested questions in modern astrophysics, and answering it requires finding the luminous ones, the halos that did manage to form stars, and working backward from their abundance to infer the total population. This means that the faintest galaxies we observe today are not simply the runts of the galactic litter, they are fossils from the earliest epoch of galaxy formation. Relics of the first dark matter structures to cross the mass threshold and form stars, likely within the first billion years after the Big Bang. Their stars are among the oldest in the universe, forged from gas that was barely enriched beyond its primordial composition. They carry chemical fingerprints of the very first supernovae. They are direct windows into the conditions that prevailed when the universe was still assembling its first structures, and they are windows into dark matter itself. Because ultrafaint dwarfs are almost entirely dark matter dominated, their internal dynamics serve as direct probes of dark matter behavior on the smallest scales. The density profiles of their halos, the minimum halo mass at which star formation becomes possible, their survival rates against tidal disruption by host galaxies, all of these observables place constraints on what dark matter particles can and cannot do. Warm dark matter, which predicts fewer small halos than cold dark matter. Fuzzy dark matter, which creates halos with diffuse cores rather than dense cusps. Self-interacting dark matter, which allows dark matter particles to scatter off each other and reshape the inner structure of halos. Each alternative model makes different predictions about how many ultra-faint dwarfs should exist, how dense their central halos should be, and how small the smallest galaxy can get before the concept breaks down. The tiniest galaxies are not astronomical curiosities filed away in catalogues and forgotten. They are among the most powerful tests of fundamental particle physics available to observational astronomy. By the early 2020s, the census of Milky Way satellites had grown to roughly 60 known objects, a mix of confirmed dwarf galaxies, confirmed star clusters, and a growing number of ambiguous systems occupying the classification grey zone. Deep imaging surveys kept probing fainter, pushing toward the detection limits of current instrumentation. But even the most extreme known objects, Segway 1, Willman 1, Tucana 2, still contained at least a few hundred visible stars and had luminosities of a few hundred solar luminosities or more. Researchers wondered whether they were approaching the bottom of the luminosity function, the faintest galaxies the universe was capable of producing, or whether an entirely new population of even smaller systems lurked below the detection threshold. Then, in 2024, a survey operating from the summit of Mauna Kea in Hawaii found something that rendered everything that came before comparatively normal. It was a system so faint that its total light output was only 11 times the luminosity of our Sun. It contained roughly 60 stars. Its total stellar mass was approximately 16 solar masses. It was 4 to 5 times less massive than the next faintest Milky Way satellite ever recorded. Its physical size was typical for a compact globular cluster, and the initial velocity measurements hinted that it might be sitting inside a dark matter halo weighing roughly 1 billion times more than all its visible stars combined. Even its name reflects the confusion. The system carries 2 designations simultaneously, Ursa Major III and Unions. One because the scientific community cannot yet determine what it is. One name assumes it is a galaxy, the other assumes it is a star cluster. What happened when astronomers pointed the most powerful spectroscopic instruments on Earth at this barely visible smudge of ancient starlight, is a story that would shake the boundary between galaxy and star cluster harder than anything that came before. The summit of Mauna Kea on the island of Hawaii rises nearly 14,000 feet above the Pacific Ocean. At that altitude, the air is thin and dry, and the sky is so transparent that starlight arrives with a clarity unmatched by almost any other location on Earth. Perched near the summit sits the Canada-France-Hawaii telescope, a 3.6-meter reflector that has been surveying the sky since 1979. It is not the largest telescope on the mountain. The twin Keck telescopes, each with 10-meter mirrors, tower nearby. The Subaru telescope, the Gemini North Observatory, and several others share the summit. But the Canada-France-Hawaii telescope possesses a particular advantage that makes it indispensable for a certain kind of science. Its wide-field imaging camera, called megacam, can photograph an area of sky roughly 1 degree across in a single exposure. This combination of depth and breadth makes it an ideal instrument for finding things that are faint, diffuse, and spread across large patches of sky, exactly the kind of object that disappears in the narrow gaze of a larger, more powerful telescope focused on a pinpoint field of view. In the mid-2010s, the Canada-France-Hawaii telescope joined a collaborative imaging campaign called the Ultraviolet Near-Infrared Optical Northern Survey, known by its acronym UNIONS. The survey pooled data from 3 telescopes across Hawaii: the Canada-France-Hawaii telescope on Mauna Kea, the Pan-STARRS telescope on Haleakala in Maui, and additional infrared observations from other facilities. The goal was sweeping: map the northern sky to a depth sufficient to resolve individual faint stars at distances of tens of thousands of light-years, creating a census of the Milky Way's stellar halo and its population of satellite companions. UNIONS was designed not to find bright objects, but to find the almost invisible ones, the faint smudges, the statistical whispers hiding in fields crowded with foreground stars. Detecting an ultra-faint satellite galaxy or an ultra-faint star cluster is not like spotting a new star through a telescope. There is no single bright point of light to notice. There is no dramatic nebula or conspicuous concentration of stars that jumps out of an image. What you are looking for is a faint statistical excess, a region of sky where the density of faint, old, metal-poor stars is slightly higher than what the Milky Way's own stellar halo would produce by chance. The signal is buried in noise. To extract it, astronomers use a technique called matched filter analysis. They construct a model of what a very old, very metal-poor stellar population would look like at a given distance, including specific predictions for the brightnesses and colours of stars along the main sequence and the red giant branch. Then they scan the survey data, pixel by pixel, looking for patches where real stars cluster in colour magnitude space in a way that matches the predicted model. Most patches show nothing. The filter finds no excess, but occasionally, in one small area of sky, a concentration appears, a handful of stars whose colours, magnitudes, and spatial positions are all consistent with a single ancient stellar population at a specific distance. That concentration is a candidate. The difficulty of this search cannot be overstated. The Milky Way's own stellar halo is not empty. It contains tens of millions of stars scattered at various distances, spanning a wide range of ages, metallicities, and luminosities. Any patch of sky observed at survey depth contains hundreds of foreground halo stars, whose colours and magnitudes partially overlap with those of a hypothetical, ancient, metal-poor satellite population at a similar distance. The signal you are hunting for is not a cluster of stars that stands out visually against a clean background. It is a statistical excess of perhaps a few dozen stars sprinkled across a region already populated by unrelated foreground objects whose photometric properties are only subtly different from those of the target. You are trying to find 60 particular grains of sand on a beach by arguing that, in one small patch, the grains are packed 3% more tightly than the background average, and that this excess is not a random fluctuation, but a real physical structure. The matched filter algorithm quantifies this. It assigns a probability to each star based on how closely its colour and magnitude match the predicted isochrone of an old metal-poor population at a given distance. Stars that match well receive high weights. Stars that do not match receive low weights. The algorithm then searches for spatial concentrations of high-weight stars that exceed the expected density of false positives from the foreground population. The threshold for detection is typically set at a statistical significance of 5 sigma or higher, meaning the observed concentration has less than a 1 in a million probability of arising by chance from the foreground alone. Even after a candidate passes this threshold, confirmation is not automatic. A 5 sigma photometric detection could still be a chance alignment of unrelated foreground stars whose colors happen to mimic the target population. It could be a tidal debris stream from a disrupted satellite that is not gravitationally bound. It could be an artifact of spatially varying survey depth, where a patch of sky observed under slightly better conditions produces a spurious overdensity. Before investing hours of precious spectroscopic time on a 10-meter telescope, the discovery team must cross-check the detection against independent photometric datasets, verify that the candidate stars share consistent proper motions using astrometric data from the Gaia space mission, and examine whether the spatial distribution of candidate members is physically plausible for a bound system rather than an elongated stream or a patchy foreground fluctuation. Ursa Major, 3 unions. 1 passed every check, its candidate members clustered tightly in color magnitude space along a single old metal pore isochrone. Their spatial distribution was compact and approximately round, consistent with a gravitationally bound system. And critically, the Gaia proper motions of the brightest candidates confirmed that they were co-moving through space as a coherent group, ruling out a chance alignment of unrelated halo field stars traveling in random directions. Simon Smith, a graduate student at the University of Victoria, applied this technique to the Union's dataset. The matched filter scan returned a detection in the constellation Ursa Major, not far from the stars that form the familiar shape of the Big Dipper. The concentration was extraordinarily faint. It consisted of roughly 60 stars, tightly clustered in both their positions on the sky and their locations in color magnitude space. The stars were consistent with a stellar population older than 10 billion years, with a mean metallicity of approximately -2.2 on the iron to hydrogen scale, meaning their iron content was roughly 160 times lower than our Sun's, a composition characteristic of stars that formed in the earliest epochs of the universe. The distance to the system was estimated at approximately 10 kiloparsecs from the Sun, or roughly 33,000 light-years. In galactic terms, this is remarkably close. It is well within the Milky Way's own halo. The object was not a distant extragalactic discovery. It was practically next door. The measured properties were staggering. The system's total luminosity was approximately 11 solar luminosities. 11. Not 11,000, not 11 million. 11 times the light of our Sun. If you could somehow replace our Sun with this entire stellar system, swapping a single star for the combined output of roughly 60, the change in brightness as seen from Earth would be modest. Our Sun is an ordinary star of average luminosity. This entire system was barely brighter. Hochu. The estimated total stellar mass was approximately 16 solar masses, with an uncertainty of +6 and -5. 16 suns worth of material total across all 60 or so stars. Most of those stars are dim red dwarfs and ancient main sequence stars of extremely low mass, contributing almost nothing to the total light output. The system's physical size was compact, a half-light radius of approximately 3 parsecs, or roughly 10 light-years. This is small, very small. For comparison, the nearest star to our Sun, Proxima Centauri, lies approximately 1.3 parsecs away. The half-light radius of this system, at roughly 3 parsecs, is barely more than twice the distance between our Sun and its nearest stellar neighbour. Within this compact volume, an entire candidate galaxy concentrates roughly half of all its light. This combination of properties, extreme faintness, tiny stellar mass, compact size, immediately placed the system in uncharted territory. It was roughly 4 to 5 times less massive than the next faintest known Milky Way satellites, a pair of objects called Kim 3 and Delve 5. It was approximately 10 times fainter than the faintest confirmed ultra-faint dwarf galaxies. It was also approximately 10 times fainter than the least luminous known globular cluster. Nothing previously discovered occupied this corner of parameter space. The object sat alone at the extreme end of every relevant axis. The faintest, the least massive, the most extreme. Its compact size was consistent with known globular clusters. Its luminosity was not consistent with anything. The object needed a name, and here the naming convention revealed the depth of the uncertainty. Newly discovered dwarf galaxies orbiting the Milky Way are traditionally named after the constellation in which they appear. Newly discovered star clusters are traditionally named after the survey that found them. Because the classification was genuinely unknown, the system received both names simultaneously. Ursa Major III, the dwarf galaxy designation, and Unions 1, the star cluster designation. This dual naming was not a bureaucratic formality. It was a public acknowledgement by the discovery team that they could not tell what they had found. The next step was spectroscopy. Imaging alone can tell you where an object is, how bright it is, and roughly what kind of stars it contains. But it cannot tell you how those stars are moving. To measure internal motions, astronomers need spectra, detailed measurements of starlight broken into its component wavelengths, allowing precise determination of each star's radial velocity through the Doppler shift. Blue shift means the star is approaching. Red shift means the star is receding. The precision required is extraordinary. Differences of a few kilometers per second, tiny fractions of a star's total orbital speed, carry the entire weight of the classification. Smith and colleagues obtained spectroscopic observations with the 10-meter Keck 2 telescope on Mauna Kea using the DEIMOS multi-object spectrograph, an instrument capable of observing dozens of stellar spectra simultaneously. From these observations, they identified 11 stars whose radial velocities were consistent with membership in the system. 8 of those 11 also had proper motion measurements from the Gaia space mission, confirming that they were co-moving through space as a coherent group. This was critical confirmation. The system was not an optical illusion or a chance alignment of unrelated foreground stars. It was a real, gravitationally bound structure. From the 11 radial velocity members, Smith's team derived an intrinsic velocity dispersion of approximately 3.7 kilometers per second, with an uncertainty range of plus 1.4 and minus 1.0. For a system containing only 16 solar masses of visible stars, this velocity dispersion was enormous. Apply the virial theorem, the fundamental relationship between kinetic energy and gravitational potential energy, in a system in equilibrium, and you get a mass estimate in the hundreds of thousands of solar masses. The implied mass-to-light ratio would be in the thousands. If the measurement was correct and reflected the true gravitational potential, the system would be overwhelmingly dominated by dark matter. The visible stars would constitute a negligible fraction of the total mass. Ursa Major, 3 unions. 1 would not just be an ultra-faint dwarf galaxy, it would be the darkest galaxy ever discovered, the system with the highest ratio of dark matter to visible matter ever measured. But Smith and colleagues were careful. They flagged their own result with explicit caveats, cautioning against overinterpretation. The velocity dispersion measurement was fragile. It depended sensitively on the inclusion of 2 stars with velocities that deviated significantly from the systemic mean. Remove the single largest velocity outlier, and the dispersion dropped to approximately 1.9 kilometers per second, still potentially significant, but far less dramatic. Remove a second outlier, and the dispersion became statistically unresolved, consistent with 0 internal spread beyond measurement errors. The difference between a dark matter-dominated galaxy and a mundane star cluster hinged on whether 1 or 2 individual stars were genuine fast-moving members of the system, or binary stars whose orbital velocities were contaminating the measurement. Binary stars are the persistent saboteurs of ultra-faint dwarf galaxy research. When 2 stars orbit each other in a close pair, the radial velocity of each star oscillates as it swings toward and away from the observer during each orbit. A single spectroscopic observation captures one instantaneous velocity, but that velocity includes both the star's motion within the larger system and its orbital motion around its binary companion. If the binary period is short, the orbital velocity can be several kilometers per second, easily large enough to inflate the apparent velocity dispersion of the entire system. The only way to disentangle binary motion from genuine systemic motion is to observe the same star multiple times across different epochs. If its velocity changes significantly between observations, it is likely a binary. If it remains stable, it is more likely a single star whose velocity reflects the gravitational potential of the host system. Smith's initial observations were single epoch. There were no repeat measurements. The binary contamination risk was acknowledged but unresolved. A companion study, coordinated with the Discovery team and published shortly afterward, took the investigation a step further. Raphael Irani, then at Carnegie Mellon University, and collaborators used N-body simulations to model the tidal evolution of the system as it orbits the Milky Way. The question was straightforward. Can a self-gravitating cluster of 16 solar masses survive on this orbit? The orbit itself had been determined using the system's position, radial velocity, and Gaia proper motions. It is a halo-like trajectory, plunging as close as approximately 13 kiloparsecs from the Milky Way's center at pericenter and swinging out to roughly 30 kiloparsecs at apocenter. The radial orbital period is approximately 0.4 billion years. At pericenter, the system passes deep into the Milky Way's gravitational domain, where tidal forces are intense. The Milky Way's gravity pulls harder on the near side of the system than on the far side, creating a stretching effect that strips stars from the outer regions and gradually unbinds the structure. Irani's simulations model the system as a self-gravitating cluster stars held together only by their own mutual gravity, with no dark matter, and evolved it forward through the Milky Way's tidal field. The results were unambiguous. Every self-gravitating model, regardless of initial mass, fully disrupted within roughly 0.6 billion years from the present, less than 2 orbital periods. The system would be torn apart within a cosmically brief interval. This was not surprising. The mean density of a 16 solar mass cluster, compressed into a 3-parsec half-light radius, is comparable to the mean density of the Milky Way itself, enclosed within the pericentric radius. The system is not significantly denser than its tidal environment. Tidal forces overwhelm it. To understand what tidal disruption means physically, consider what happens each time the system reaches pericenter, its closest approach to the Milky Way's center, roughly 13 kiloparsecs from the core. At this distance, the Milky Way's gravitational field is intense. The circular velocity of the galaxy at this radius is approximately 240 kilometers per second, reflecting the enormous mass enclosed within that sphere. The tidal field at pericenter does not simply tug gently on the system from one direction, it creates a differential force. The near side of the cluster is pulled more strongly toward the galactic center than the far side, and simultaneously the far side is pushed outward by the centrifugal component of the orbital motion. This stretching force acts like a pair of invisible hands pulling the system apart along the axis connecting it to the Milky Way's center. For a massive, dense system like a typical globular cluster, 100,000 solar masses compressed into a few parsecs, the internal gravity easily overpowers the tidal stretching. The cluster passes through pericenter, loses a handful of loosely bound outer stars, and continues intact. But for a system containing only 16 solar masses spread across 3 parsecs, the internal gravity is feeble. The tidal forces at pericenter are comparable in strength to the self-gravity holding the system together. Each passage strips away a significant fraction of the remaining stars. The process is cumulative and irreversible. Stars lost to tidal stripping do not return. They trail behind and ahead of the system along its orbit, forming tidal tails that gradually disperse into the Milky Way's halo. Irani's simulations tracked this process in detail. They varied the initial mass of the self-gravitating cluster across a wide range, from just above the current observed mass up to several hundred solar masses, testing whether a more massive progenitor could survive longer by starting with a larger reservoir of stars to lose. The result was unequivocal. Regardless of initial mass, every self-gravitating model reached complete disruption within roughly 0.6 billion years, less than 2 full orbital cycles. The system would dissolve entirely, its stars scattered along a tidal stream wrapping around the Milky Way. No self-gravitating configuration survived. This created a powerful argument. The stars in Ursa Major III Unions 1 are older than 10 billion years. The system has presumably been orbiting the Milky Way for many billions of years, completing dozens of orbits through the tidal danger zone near pericenter. If it were self-gravitating, with nothing but its own stellar mass holding it together, it should have been destroyed billions of years ago. The fact that it still exists as a coherent, bound structure strongly suggests that something additional is stabilizing it. Something providing a gravitational well deep enough to resist the Milky Way's tidal forces across many orbital periods. The natural candidate is dark matter. Iranian colleagues explored what kind of dark matter halo could plausibly host such a system. Within the lambda cold dark matter framework, the first dark matter halos to form stars are expected to have virial masses of roughly 100 million to 1 billion solar masses, depending on the epoch of formation and the strength of reionization feedback. A halo at the lower end of this range, formed at a redshift of approximately 2 corresponding to roughly 11 billion years ago, consistent with the inferred stellar age, would develop a central density profile following the Navarro-Frenk white form, with a dense, cuspy core that resists tidal stripping far more effectively than a uniform distribution of mass. The simulations showed that if Ursa Major III formed at the center of a cuspy dark matter halo, with a virial mass of roughly 1 billion solar masses, the halo's dense core would survive the Milky Way's tidal field. Over many billions of years and dozens of pericentric passages, the outer layers of the halo would be gradually stripped away, but the innermost region, where the stars reside, would remain intact. The predicted velocity dispersion for stars embedded in such a surviving remnant halo would be approximately 1 kilometer per second. This prediction was broadly consistent with the observed velocity dispersion range between roughly 1 and 4 kilometers per second, depending on which stars were included, though it fell below the nominal best fit value of 3.7. The implications, if correct, were extraordinary. A 1 billion solar mass dark matter halo containing only 16 solar masses of stars would represent a mass ratio of roughly 60 million to 1. For every unit of visible matter, there would be 60 million units of dark matter. This would eclipse the mass-to-light ratios of every other known galaxy by an enormous margin. Segue 1, with its mass-to-light ratio of roughly 1,000 to 3,000, would seem almost star-rich by comparison. Ursa Major III would be a galaxy in which the visible component is so negligible that the system is, for all practical gravitational purposes, a pure dark matter object with a few ancient stars sprinkled through its center as witnesses to its existence. This prospect electrified the astrophysics community for reasons that extended well beyond the record-breaking statistics. If a dark matter halo of 1 billion solar masses could host a galaxy with only 16 solar masses of stars, it meant that the minimum luminosity for galaxy formation was far lower than anyone had previously measured. It meant that the universe could produce galaxies that are functionally invisible systems containing dark matter, halos of enormous mass, but so few stars that they are undetectable by any existing survey unless they happen to sit extremely close to us. Ursa Major III unions. One is only 10 kiloparsecs from the Sun. If it were located at the distance of most known ultrafaint dwarfs 50 to 100 kiloparsecs, it would be completely undetectable with current technology. This raised the unsettling possibility that the Milky Way might be surrounded by hundreds or thousands of similar objects, dark matter halos containing only a handful of ancient stars, lurking below the detection threshold in every direction. It also placed severe pressure on alternative dark matter models. Fuzzy dark matter, a model proposing that dark matter consists of extremely light particles with de Broglie wavelengths comparable to the size of dwarf galaxy cores, predicts that halos below a certain mass cannot form dense central concentrations. The extremely high inferred density of the Ursa Major III dark matter halo, if confirmed, would be very difficult to reconcile with standard fuzzy dark matter models. Warm dark matter models, which predict fewer small halos than cold dark matter, would also face constraints. Self-interacting dark matter, which tends to create constant density cores rather than cuspy centers, would struggle to produce the dense inner profile needed to survive tidal stripping on such a tight orbit. Each alternative dark matter model would need to explain how this system exists, and for several models, explaining it would be extremely difficult or impossible. The theoretical community responded rapidly. Papers analyzing the implications for dark matter physics appeared within weeks of the discovery. Groups calculated predicted gamma-ray signals from dark matter annihilation in the dense core. Others modeled the expected tidal tails that should extend from the system if it was undergoing even mild stripping. The object's extreme proximity to the Sun made it the closest known galaxy candidate, if it was indeed a galaxy, offering a laboratory for dark matter studies at a distance no other system could match. Within months, multiple independent groups published analyses exploring the system's implications across different branches of dark matter physics. Several teams calculated the expected gamma-ray flux from dark matter particle annihilation at the system's inferred central density. If the dark matter halo was as dense as the velocity dispersion suggested, the annihilation rate would be extraordinarily high per unit volume, and the system's proximity only 10 kiloparsecs away would make the signal potentially detectable by the Fermi Large Area Telescope. The predicted flux depended sensitively on the halo's inner density slope, with cuspy Navarro-Frank white profiles yielding signals orders of magnitude stronger than chord profiles. A detection would not merely confirm the presence of dark matter, it would constrain the annihilation cross-section of dark matter particles, a fundamental parameter in particle physics that no laboratory experiment has yet been able to measure. Other groups examined the implications for the minimum halo mass capable of forming a luminous galaxy. If a halo of roughly 1 billion solar masses can produce a galaxy containing only 16 solar masses of stars, then the overwhelming majority of the halo's baryonic budget was never converted into visible stars at all, a formation efficiency so low it challenges the most pessimistic models of how star formation shuts down in the smallest halos. This efficiency is far below what even the most pessimistic models of reionization feedback had predicted. It would imply that star formation in the smallest halos is not merely suppressed but almost entirely extinguished, with only a vanishing trace of baryonic matter managing to cool, collapse, and ignite nuclear fusion before the gas is heated beyond recovery. Still others examined what the system's density would mean for fuzzy dark matter, finding that standard fuzzy dark matter particle masses in the range of 10 to the negative 22 electron volts would produce halo cores too diffuse to match the inferred central density, potentially ruling out a significant portion of the fuzzy dark matter parameter space if the galaxy interpretation held. But all of these implications rested on a single unstable foundation: the velocity dispersion measurement. If the dispersion of 3.7 kilometers per second was accurate, the dark matter case was strong. If the true dispersion was closer to 1.9, the value obtained when the single largest outlier was removed, the case was still plausible but weaker, and the mass-to-light ratio dropped significantly. If the dispersion was unresolved, consistent with zero, then there was no kinematic evidence for dark matter at all. The system could be a self-gravitating star cluster, and the tidal survival problem would need to be explained through some other mechanism, perhaps a population of unseen stellar remnants adding mass, or perhaps a recent formation scenario in which the system had not yet completed enough orbits to disrupt. Everything depended on what happened when astronomers returned to the Keck 2 telescope with a new plan. They needed multi-epoch observations, the same stars measured again, months or years later, to check for binary velocity variations. They needed higher spectral resolution, sharper measurements of each star's velocity to reduce the per-star uncertainty that blurred the dispersion estimate. And they needed chemical abundances, precise metallicities for individual stars to determine whether the system showed the chemical enrichment spread expected of a galaxy or the chemical uniformity expected of a cluster. The initial discovery had identified the most extreme Milky Way satellite ever found. It had shown that the object either contained dark matter in quantities that would make it the darkest galaxy in the known universe, or that it was the faintest self-gravitating star cluster ever seen, an object whose survival against tidal destruction would require its own explanation. The two possibilities were not merely different answers to the same question. They pointed toward fundamentally different conclusions about how the universe builds structure at the smallest scales, how dark matter behaves in the lowest mass halos, and whether the word galaxy can stretch to cover a system containing fewer stars than a typical open cluster in the Milky Way's disk. The Discovery team knew that only new data could resolve the tension. They had planted a flag at the extreme boundary of observational astronomy, at the threshold where 60 ancient stars either sit inside an invisible dark matter mountain or drift alone through the tidal violence of the Milky Way's gravitational field, bound only to each other and to whatever unseen remnants might share their tiny volume of space. What came back from the follow-up campaign did not settle the question the way anyone expected. It shifted the weight of evidence in a direction that made the story more complicated, not less. William Cerny had been studying the faintest satellites of the Milky Way for years before Ursa Major III Unions 1 appeared in the data. As a graduate student and then postdoctoral researcher at Yale University, he had built a career around the objects that live at the classification boundary, the systems too faint for easy answers, too ambiguous for confident labels. He understood better than most how fragile velocity dispersion measurements become when the entire calculation rests on a handful of stars. And he understood that the extraordinary claim attached to Ursa Major III Unions, one that it might be the darkest galaxy in the known universe, demanded extraordinary scrutiny. The follow-up campaign began with a return to the Keck Observatory on Mauna Kea. Cerny and collaborators used two instruments across the twin Keck telescopes, Deimos on Keck 2, the same multi-object spectrograph that had provided the original velocity measurements, and LRIS on Keck 1, the low-resolution imaging spectrometer, which offered complementary capabilities for measuring chemical abundances through different spectral features. The goal was twofold. First, obtain new velocity measurements for the known member stars, ideally at multiple epochs separated by months, to check for binary-induced velocity variations. Second, measure the chemical compositions of individual stars with enough precision to determine whether the system displayed a metallicity spread consistent with a galaxy or the chemical uniformity expected of a star cluster. The new observations expanded the confirmed member sample. Cerny's team identified a 12th star as a radial velocity member, bringing the total to 12 stars with secure membership. More importantly, the new velocity measurements carried substantially improved precision. The original Smith, et al. Data had per-star velocity uncertainties that, while adequate for identifying members, left room for significant ambiguity in the dispersion calculation. The new data sharpened these measurements considerably, reducing the individual uncertainties and providing a cleaner foundation for the statistical analysis. The results overturned the original picture. When Cerny and collaborators applied Bayesian analysis to the updated velocity dataset incorporating the expanded member sample, the improved per-star precisions, and a careful treatment of binary contamination, the velocity dispersion came back dramatically lower than the initial estimate. The analysis favored a value of approximately 0.1 kilometers per second. The 95% credible upper limit was 2.3 kilometers per second. The original value of 3.7 kilometers per second, the measurement that had launched the darkest galaxy hypothesis, was now ruled out by the new data. This was not a subtle revision. It was a near-complete inversion of the kinematic evidence. The original measurement had implied a mass-to-light ratio in the thousands, requiring an enormous dark matter halo to explain the stellar motions. The new measurement implied little to no excess mass beyond the stars themselves. The gravitational signature of dark matter, which had seemed so promising in the initial data, had largely disappeared. What caused such a dramatic shift? The answer involved exactly the culprit that the Discovery team had warned about: binary stars. One of the 11 original member stars had been flagged by Smith and colleagues as a suspected spectroscopic binary, a star whose velocity appeared inconsistent across different spectral lines or observing conditions. The new multi-epoch observations confirmed this suspicion. The star's velocity had changed substantially between the original measurement and the follow-up, consistent with orbital motion around an unseen companion. This single binary, when included in the dispersion calculation, had inflated the velocity spread of the entire sample. Remove it, and the dispersion drops. The new data also identified 3 additional binary candidates among the member stars, further complicating the picture. In a system containing only 12 confirmed members, even a few binaries can dominate the statistics. Each contaminated velocity measurement pulls the calculated dispersion upward, mimicking the gravitational signature of dark matter where none may exist. Binary contamination is a fundamental challenge that shapes every result at this luminosity frontier. In a massive galaxy containing millions of observable stars, it averages out. For every binary moving toward the observer, another moves away. The net effect on the overall dispersion is negligible, but in a system with 12 members, the law of large numbers does not apply. One or two binaries with unfavorable orbital phases at the moment of observation can shift the calculated dispersion by a factor of 2 or more. The statistical machinery is simply not robust at such small sample sizes. Every individual data point carries disproportionate weight, and every individual binary carries disproportionate risk. Cerny's team went further. Having addressed the kinematic evidence, they turned to the second major diagnostic, metallicity. Using the LRIS spectrograph, they obtained measurements of the calcium-2K absorption line for the 12 brightest confirmed members. Calcium-2K is a strong spectral feature that serves as a reliable proxy for overall iron abundance in metal-poor stars. By measuring the strength of this line in each star, Cerny and collaborators could estimate individual stellar metallicities and crucially determine whether those metallicities were uniform or spread across a range. The results reinforced the kinematic finding. The 12 stars showed no evidence of significant internal metallicity variation. The metallicities were uniformly low, centered around an iron-to-hydrogen ratio of approximately -2.2, with a spread consistent with measurement uncertainty alone. The upper limit on the intrinsic metallicity dispersion was small, far smaller than the typical metallicity spreads of 0.3 to 0.7 dex, observed in confirmed ultra-faint dwarf galaxies, where multiple generations of star formation create chemically distinct populations. Instead, the chemical uniformity of Ursa Major III unions, one more closely resembled the nearly homogeneous compositions seen in ancient globular clusters, where all stars formed in a single episode from the same parental gas cloud, and no subsequent enrichment occurred within the system. This was the second pillar of the galaxy hypothesis crumbling. The first pillar, elevated velocity dispersion, implying dark matter had fallen to binary contamination and improved measurements. The second pillar, metallicity spread, implying chemical self-enrichment within a deep potential well, had failed to appear in the data at all. Neither of the two primary diagnostics used to distinguish galaxies from star clusters at ultra-faint luminosities supported the galaxy interpretation. Cerny and collaborators drew a careful conclusion. Based on the available evidence, they stated that Ursa Major III unions, one is more consistent with a star cluster than with an ultra-faint dwarf galaxy. They noted that there are no confirmed dwarf galaxies for which both the velocity dispersion and the metallicity dispersion are as low as the limits measured for this system. Every confirmed ultra-faint dwarf has at least one clear indicator, either a resolved velocity dispersion significantly exceeding what its visible stars can account for, or a metallicity spread demonstrating chemical self-enrichment across stellar generations, or both. Ursa Major III Unions 1 shows neither, but Cerny's team also exercised restraint. They did not declare the galaxy hypothesis dead. They acknowledged explicitly that the measurements could not fully rule out the presence of dark matter. The velocity dispersion upper limit of 2.3 kilometers per second, while dramatically lower than the original estimate, is not zero. A modest dark matter halo could still produce a dispersion within this range without exceeding the upper bound. And the metallicity dispersion limit, while small, rests on measurements of only 12 stars, a sample that could miss a subtle chemical spread if it exists among fainter, unmeasured members. The dwarf galaxy scenario remains viable, pending higher resolution chemical abundance patterns and even tighter multi-epoch kinematic constraints. The paper's title captured the measured tone of the conclusion: no observational evidence for dark matter, nor a large metallicity spread in the extreme Milky Way satellite, Ursa Major III Unions 1. Not a definitive rejection of the galaxy hypothesis. An absence of positive evidence for it. A distinction that matters enormously in a field where classification often depends on which uncertainty you find more tolerable. The shift in evidence did not eliminate the mysteries surrounding the system. It rearranged them. If Ursa Major III Unions 1 is not a dark matter-dominated galaxy, a new question immediately takes the stage. How has it survived? The tidal survival problem identified by Irani and collaborators in 2024 remains. A self-gravitating cluster of 16 solar masses on this orbit should be destroyed by the Milky Way's tidal field within a cosmically brief interval. The stars are old. The orbit has been repeating for billions of years. If nothing but the mutual gravity of 16 solar masses of stars holds the system together, It should have been torn apart long ago. Removing dark matter from the explanation does not remove the need for an explanation. Something must still be stabilizing the system, or else its survival requires an improbable coincidence of timing. The possibility that we happen to have Rostami Shirazi and collaborators, in a study published in 2025, used N-body simulations to model this scenario explicitly. They found that a dark matter-deficient progenitor, a cluster that never sat inside a dark matter halo, could reproduce the current observed properties of Ursa Major III unions. 1. If it retained a significant population of stellar mass black holes with relatively weak natal kicks. In this model, the black holes provide the gravitational glue that dark matter was originally invoked to explain. The system survives tidal disruption not because it sits inside an invisible halo of exotic particles, but because it harbors an invisible population of dead stars, massive enough to deepen its gravitational well. This scenario is physically plausible. Observations of other low-mass stellar systems have provided growing evidence that black hole retention is more common than traditionally assumed. Gravitational wave detections of merging black hole binaries by the LIGO and Virgo observatories have revealed a population of stellar mass black holes spanning a broad range of masses, some of which formed in dense stellar environments. If even a modest number of such objects remain bound within Ursa Major III Unions 1, their combined mass could exceed the visible stellar mass by a significant factor, stabilizing the system without requiring dark matter. The dark star cluster model also offers a natural explanation for the inflated velocity dispersion in the original data. If unseen compact remnants contribute substantial mass to the system, they deepen the gravitational potential well. Stars embedded in that deeper well move faster than they would in a system composed solely of visible stars. Even without dark matter, the presence of black holes and neutron stars could produce a velocity dispersion moderately above what 16 solar masses of luminous stars would predict. This intermediate scenario, no dark matter, but significant remnant mass occupies the space between the two extremes that dominated the initial debate. But the dark star cluster model has its own uncertainties. The number and mass distribution of retained black holes depend on assumptions about the initial mass function of the system's first stellar generation, the physics of black hole natal kicks, and the dynamical history of the cluster over 10 billion years. These parameters are poorly constrained for an object this faint and this old. The model is consistent with the data. It is not uniquely required by it. Ursa Major III unions. One is not the only system haunting this classification boundary. It is the most extreme example, but it belongs to a growing population of ambiguous satellites that resist clean categorization. Understanding why it matters requires seeing it in the context of these other contested objects. Willman 1, discovered in 2005 in the Sloan Digital Sky Survey data, was among the first systems to expose how messy the classification boundary could become. Located approximately 38 kiloparsecs from the Sun, it was initially reported to have a high velocity dispersion consistent with dark matter domination, but its systemic velocity was dangerously close to the velocities of Milky Way foreground stars at similar positions in the sky, meaning that contamination from unrelated halo stars could easily corrupt the membership list. Different research groups analyzed the same data and reached opposite conclusions. Some found a resolved velocity dispersion, indicating dark matter. Others, after applying stricter membership criteria that removed likely interlopers, found a dispersion consistent with no dark matter at all. The debate simmered for years without resolution. Willman 1 eventually received a tentative galaxy classification based partly on an apparent metallicity spread among its members, but even this evidence was questioned as potentially arising from foreground contamination. The object remains one of the most contentious in the field. Tucana 3, a satellite discovered in the Dark Energy Survey, presented a different kind of ambiguity. Its velocity dispersion was consistent with dark matter, but its tidal tails, streams of stars being stripped by the Milky Way's gravity, suggested it was undergoing active disruption. Tidal disruption can inflate a system's apparent velocity dispersion by injecting kinetic energy into the stellar motions, mimicking the signature of a dark matter halo, where the true source is external gravitational torque. Disentangling the internal dispersion from tidal effects requires sophisticated modeling that depends on assumptions about the system's orbit, its initial structure, and the Milky Way's gravitational potential. The classification of Tucana 3 remains dependent on which model one trusts. Delve 1, Eridanus 3, and several other recently discovered ultra-faint compact satellites occupy similar positions in parameter space. Each sits in the region where the physical sizes, luminosities, and velocity dispersions of the smallest dwarf galaxies overlap with those of the faintest star clusters. Each requires case-by-case analysis that is limited by small sample sizes, binary contamination risks, and the fundamental difficulty of measuring precise velocities and chemical abundances for a few dozen extremely faint stars at distances of tens of kiloparsecs. These are not isolated puzzles, they form a pattern. The boundary between galaxy and star cluster is not a wall, it is a fog bank. Objects enter it from both sides. Star clusters that appear unusually massive for their luminosity, dwarf galaxies that appear unusually faint for their implied dark matter content. Somewhere inside this fog, the clean distinction between dark matter-dominated and baryon-only systems dissolves into measurement uncertainty, binary contamination, tidal effects, and the irreducible limitations of trying to characterize a gravitational system using the motions of 8 or 12 or 20 stars. Why does any of this matter beyond the specialized world of stellar dynamics and satellite taxonomy? The answer extends far beyond classification for its own sake. If Ursa Major III Unions 1 is a galaxy, if future measurements reveal that it does sit inside a dark matter halo, despite the current absence of kinematic and chemical evidence, the implications for dark matter physics are profound. It would mean that dark matter halos of substantial mass can produce galaxies with absurdly small stellar populations, pushing the minimum luminosity for galaxy formation to limits that severely constrain the particle nature of dark matter. Warm dark matter models, which suppress the formation of small halos, would face significant tension. Fuzzy dark matter models, which create diffuse halo cores incapable of surviving strong tidal fields, would struggle to explain how such a dense system persists on such a punishing orbit. The measurement would sharpen the case for cold dark matter at the smallest scales, precisely where alternatives have traditionally claimed the most leverage. If, instead, the system is confirmed as a star cluster, a different set of implications follows. It would mean that the faintest end of the Milky Way satellite luminosity function includes objects that are not dark matter halos at all, but ancient stripped-down remnants of once larger stellar systems. This would complicate the census of dark matter subhalos and the use of satellite counts to constrain the minimum halo mass for galaxy formation. It would mean that some fraction of the ultra-faint satellites discovered in current and future surveys are not galaxies and cannot be used as dark matter laboratories. The field would need more sophisticated methods to separate genuine ultra-faint dwarfs from imposter clusters masquerading at similar luminosities. And there is a deeper practical consequence. Astronomers have used ultra-faint dwarf galaxies as targets for indirect dark matter detection experiments. Gamma-ray telescopes like the Fermi Large Area Telescope have pointed at systems including Segway 1, Draco 2, and others, searching for the faint glow of gamma rays that would be produced if dark matter particles annihilate at the dense centers of dwarf galaxy halos. The expected signal strength depends critically on the dark matter density profile, which is inferred from the velocity dispersion. If the velocity dispersion is contaminated by binaries, inflated by tidal effects, or simply measured from too few stars, the inferred dark matter density is wrong, and the predicted gamma-ray signal is wrong. Every dark matter search that uses an ultra-faint dwarf as a target relies on the assumption that the object is correctly classified as a galaxy, and that its kinematic properties accurately reflect its dark matter content. Ursa Major III Unions 1 demonstrates how tenuous those assumptions can be. Cerny and collaborators proposed a pragmatic methodological standard for the field going forward. They argued that ultra-faint, compact Milky Way satellites, with strong upper limits on both velocity dispersion and metallicity dispersion systems, for which no positive evidence of dark matter or chemical self-enrichment exists, should be regarded as star clusters until clear positive evidence proves otherwise. The burden of proof, they suggested, should fall on the galaxy hypothesis, not on the cluster hypothesis. In a regime where measurement uncertainties are large, sample sizes are small, and systematic effects like binary contamination can mimic dark matter signatures, the conservative default should be the simpler explanation. Stars held together by their own gravity, perhaps supplemented by invisible stellar remnants, without invoking a dark matter halo. This methodological proposal carries weight because it addresses a broader cultural tendency in the field. Ultra-faint dwarf galaxies are scientifically exciting. They are dark matter laboratories. They are fossil relics of the earliest epoch of galaxy formation. They attract funding, telescope time, and theoretical attention. A new ultra-faint dwarf galaxy candidate generates more interest and more follow-up than a new faint star cluster. There is an understandable, if largely unconscious, incentive to interpret ambiguous objects as galaxies rather than clusters. Cerny's proposal pushes back against this tendency by demanding that the evidence meet a clear affirmative threshold before the galaxy label is applied. But not everyone in the community agrees. Some researchers argue that the tidal survival problem is sufficiently compelling on its own to favour the galaxy interpretation, even in the absence of resolved velocity dispersion or metallicity spread. If a self-gravitating cluster cannot survive the Milky Way's tidal field for billions of years on this orbit, and if the dark star cluster model requires specific assumptions about black hole retention that remain observationally unverified, then perhaps the simplest explanation is still dark matter, even if the kinematic signal is too subtle to detect with current instruments. The absence of evidence, in this view, is not evidence of absence. A dark matter halo producing a velocity dispersion of 0.5 kilometers per second would be virtually impossible to detect with existing spectroscopic precision in a system of 12 stars. The signal could be real and simply below the noise floor. This is the crux of the dispute as it stands today. Both sides are scientifically legitimate. Both acknowledge the same data. They differ on how to interpret silence. When the measurements say neither clearly yes nor clearly no, does the default classification matter? Is the object a star cluster until proven otherwise, or a galaxy candidate whose dark matter content simply eludes current measurement precision? The answer depends partly on philosophy of science, and partly on what new data the next generation of observations will deliver. And that next generation is coming soon. What has become clear is that Ursa Major III unions, one is not merely a classification problem to be solved and filed away. It is a signpost marking the frontier where astronomy's categories begin to fail. It sits in a region of parameter space where no confirmed galaxy has ever been found, where the velocity dispersion is this low, the metallicity dispersion is this small, and the stellar mass is this negligible. Whether it turns out to be the darkest galaxy in the universe or the faintest star cluster ever seen, the object has already accomplished something that neither answer can undo. It has forced the question of what a galaxy is into the sharpest focus the field has ever known, and it has revealed that at the faintest extremes, the universe offers evidence that is quieter than our instruments can confidently hear. The deeper question is no longer just about this one system. It is about the boundary itself, what it means, where it sits, and whether it was ever as firm as astronomers believed. The word galaxy was never designed for what astronomers are now asking it to hold. The tension is not new. Every generation of astronomers has encountered objects that did not fit the categories inherited from the previous generation. But the current tension has a special character, because it touches not just what we observe, but the invisible scaffolding we believe supports everything we observe. Dark matter is the foundation of modern cosmological structure. If the line between galaxy and star cluster is ultimately a line between dark matter dominated and dark matter free, then failing to draw it cleanly means failing to map the dark matter itself. It was born in ancient Greece to describe the pale river of light arching across the night sky. It matured in the 20th century to describe vast island universes containing billions of stars. It expanded to include dwarfs, irregulars, ellipticals, and every luminous structure that carried its own gravitational identity across the cosmic landscape. At each stage, the words stretched to accommodate new discoveries. At each stage, the core intuition held. A galaxy is big, luminous, and populated with stars on a scale that dwarfs any other single astronomical object. Ursa Major. 3 unions. One sits at the point where that intuition either bends one final time or finally snaps. 60 stars, 16 solar masses, 11 solar luminosities, a volume of space 10 light-years across. If this is a galaxy, then the word has travelled so far from its origin that it now describes something that could fit inside the distance between our Sun and its nearest stellar neighbour, and still have room to spare. If this is not a galaxy, then the word has held its boundary, but the object that tested it has revealed how arbitrary that boundary always was. To understand why this matters, we need to step back from the classification debate and look at what the smallest galaxies actually teach us, not about themselves, but about the universe's deepest architectural secrets. Because the strange truth is that the tiniest galaxies are more scientifically valuable than the largest ones for answering the questions that matter most. The Milky Way contains roughly 400 billion stars, vast quantities of gas and dust, a supermassive black hole at its centre, and a dark matter halo containing approximately 10 times the mass of all its visible components combined. Separating dark matter's gravitational effects from those of ordinary matter in such a complex system is extraordinarily difficult. Stars, gas, dust, stellar remnants, molecular clouds, all of them contribute to the gravitational budget. Disentangling the dark matter signal from the baryonic noise requires sophisticated modelling that carries its own assumptions and uncertainties. The dark matter is there, its effects are measurable, but it shares the stage with a dense, complex, interacting population of visible matter that obscures the details. Now consider an ultra-faint dwarf galaxy, a system where the total stellar mass is a few hundred or a few thousand solar masses, where the gas has been stripped or exhausted billions of years ago, where there is no dust, no active star formation, no supermassive black hole, no molecular clouds. The visible matter is negligible. The baryonic contribution to the gravitational potential is a rounding error. What remains is almost pure dark matter. The stars inside such a system are not important for their own sake. They're important because they move, and their motions trace the gravitational field of the dark matter halo they inhabit with a directness that no measurement in a massive galaxy can match. Ultra-faint dwarfs are the cleanest dark matter laboratories in the observable universe. They are systems where the dark matter signal is not buried under layers of baryonic complexity. It is exposed. The velocity dispersion of a few dozen ancient stars directly probes the depth and shape of the dark matter potential well. The spatial distribution of those stars reveals the density profile of the halo's inner regions. The survival of the system against tidal disruption constrains the halo's overall mass and concentration. Each measurement, however uncertain, provides a constraint on the nature of dark matter itself, on the mass of the dark matter particle, on whether dark matter interacts with itself, on whether dark matter halos develop dense cusps or flat cores at their centers. This is why the classification of an object like Ursa Major III Unions 1 carries stakes far beyond astronomical bookkeeping. If it is a galaxy, its dark matter halo is among the densest and most extreme ever inferred. Its inferred central density, if confirmed, would challenge models of fuzzy dark matter, which predict that halos below a certain mass cannot form concentrated central cusps, because the quantum wave nature of extremely light dark matter particles smooths out structure on small scales. Reconciling fuzzy dark matter with a halo dense enough to survive the Milky Way's tidal field on the tight orbit of Ursa Major III Unions, one would require significant modifications to standard fuzzy dark matter models, or perhaps rule them out entirely at certain particle masses. Similarly, warm dark matter, a model in which dark matter particles have residual thermal velocities from the early universe that suppress the formation of small-scale structure, predicts fewer low-mass halos than cold dark matter. If the galaxy interpretation holds, it strengthens the case that dark matter is cold and that low-mass halos form abundantly, exactly as the standard lambda cold dark matter model predicts. Self-interacting dark matter presents yet another set of constraints. In models where dark matter particles scatter off each other at rates significant enough to redistribute energy within halos, the central regions of small halos are expected to develop constant density cores rather than the steep density cusps predicted by cold dark matter. A cored halo at the mass scale inferred for Ursa Major III would be more vulnerable to tidal stripping than a cuspy one. If the system has survived for billions of years on its current orbit, its halo must be dense enough at the center to resist disruption. a condition more naturally satisfied by cuspy cold dark matter profiles than by the chord profiles of self-interacting models. The survival of this system, if it is a galaxy, becomes a test of dark matter microphysics. Each of these constraints sharpens as the system in question becomes smaller and fainter. In massive dwarf galaxies containing millions of stars, the constraints are valuable but diluted by baryonic complexity and measurement averaging. In ultra-faint dwarfs like Segway 1, the constraints are cleaner but still rest on samples of a few dozen stars. At the extreme represented by Ursa Major III Unions 1, the constraint tightens to a razor's edge, but so does the risk that the entire measurement is wrong, contaminated, or misinterpreted. The power and the fragility are two sides of the same coin. This tension connects directly to one of the oldest unsolved problems in cosmology, the missing satellites problem. Lambda-cold dark matter simulations predict that a galaxy the size of the Milky Way should be surrounded by thousands of dark matter subhalos, small, gravitationally bound clumps of dark matter orbiting within the larger host halo. Many of these subhalos should be massive enough to host stars, forming satellite galaxies detectable by current surveys, but the observed count of Milky Way satellites falls far short of the theoretical prediction. As of the most recent census, approximately 60 satellites have been confirmed. Simulations predict hundreds to thousands. Where are the rest? Several explanations have been proposed, and each carries different implications for fundamental physics. The simplest resolution invokes observational incompleteness. Current surveys have not covered the entire sky to uniform depth. The Sloan Digital Sky Survey mapped roughly 1/3 of the sky. The Dark Energy Survey covered a different region in the southern hemisphere. Large portions of the sky, particularly those behind the dense stellar fields of the Milky Way's disk, remain poorly explored. Ultra-faint satellites, at distances greater than roughly 50 kiloparsecs, are beyond the detection limits of most existing surveys. The missing satellites may simply be there, waiting for deeper and wider surveys to find them. This explanation is strengthened enormously by the existence of objects like Ursa Major III Unions 1. If a system with only 11 solar luminosities can exist as a bound satellite of the Milky Way, then the detection threshold for the faintest satellites is far higher than previously appreciated. A system this faint would be completely undetectable beyond roughly 20 kiloparsecs with current instrumentation. If it were located at the typical distance of known ultra-faint dwarfs 50 to 100 kiloparsecs, no survey on Earth could find it. The Milky Way's halo could be teeming with similar objects, each containing a handful of ancient stars inside a dark matter halo of substantial mass, all hiding below the detection floor. An alternative explanation for the missing satellites invokes the physics of galaxy formation itself. Below a critical dark matter halo mass, the gravitational potential well may be too shallow to capture and cool enough gas to form stars. A specific event in the early universe, the epoch of reionization, established a mass threshold that permanently divided dark matter halos into two populations: those that had already collected enough gas to form at least some stars, and those that would remain starved and dark forever. The physics behind this threshold deserves closer attention, because it connects the existence of an object like Ursa Major III Unions 1 to conditions that prevailed across the entire universe during its first billion years. In the earliest epochs after the Big Bang, the universe was filled with neutral hydrogen and helium gas. Dark matter had already begun collapsing into halos, gravitationally bound concentrations that grew by accreting surrounding material. The gas followed the dark matter, falling into the gravitational wells of these halos and accumulating at their centers. In halos above a critical mass, the gas could cool efficiently through atomic hydrogen radiation, losing thermal energy and condensing into dense clouds that fragmented and formed stars. The first generation of stars ignited inside these halos, perhaps as early as 100 to 200 million years after the Big Bang. But star formation came with consequences. The first stars were massive, luminous, and short-lived. They poured ultraviolet radiation into the surrounding gas, ionizing the neutral hydrogen atoms and heating the intergalactic medium to temperatures of roughly 10,000 to 20,000 degrees. This process, called reionization, unfolded over several hundred million years and was largely complete by the time the universe reached an age of approximately 1 billion years, corresponding to a cosmological redshift of roughly 6. By the end of reionization, the universe had transitioned from a neutral, opaque state to an ionized, transparent one. The cosmic microwave background radiation traveled freely through this newly transparent medium, eventually reaching our telescopes as the faint afterglow of the Big Bang. Reionization transformed the gas dynamics of the universe at every scale. Before reionization, neutral gas could fall freely into dark matter halos of any mass. After reionization, the heated gas had too much thermal energy to be captured by the shallowest gravitational wells. A dark matter halo needs a circular velocity of at least roughly 15 to 20 kilometers per second, corresponding to a virial mass of roughly 100 million to 1 billion solar masses, depending on redshift and environment, to gravitationally overcome the thermal pressure of the heated intergalactic gas and pull it inward. Below this threshold, gas accretion effectively ceases. The halos still exist. They continue orbiting within the host galaxy's halo, but they are starved of the raw material needed to form stars. They become permanently dark. This is why the stars in ultra-faint dwarf galaxies are almost universally ancient. The galaxies formed their stars before reionization, during the brief window when neutral gas was still available to small halos. Once reionization swept through their region of the universe, their gas supply was cut off and star formation stopped. The stars we observe today in systems like Segway 1 and Boots 1 were born in that narrow pre-reionization window, more than 12 billion years ago, and have been passively aging ever since. These ancient populations predate most of the stellar mass in the modern universe, and their extreme chemical poverty marks them as products of the earliest star-forming halos, survivors from an era that ended before the universe reached even a tenth of its current age. The stars in Ursa Major III Unions 1 are consistent with this picture. Their estimated age exceeds 10 billion years, and their extremely low metallicity, an iron-to-hydrogen ratio of approximately -2.2, indicates that they formed from gas that had been enriched by, at most, a tiny number of prior supernovae. They carry the chemical fingerprints of a single brief burst of star formation in an environment where heavy elements were exceedingly scarce. If the system is a galaxy, its stars represent one of the most marginal star formation events the universe has ever produced. A dark matter halo that barely crossed the mass threshold, captured just enough gas, formed just enough stars to leave a visible trace, and then fell silent forever as reionization heated the surrounding gas beyond its gravitational reach. This interpretation places the system at the precise intersection of two of the most important thresholds in cosmology: the minimum dark matter halo mass for galaxy formation and the epoch of reionization that established that minimum. Understanding where these thresholds lie is essential for predicting how many luminous satellites the Milky Way should possess, and for constraining the properties of dark matter particles through the abundance of the smallest galactic structures. If this picture is correct, the missing satellites are not missing at all. They are dark. They exist as predicted by lambda cold dark matter, but they never formed stars. The observable satellite population represents only the tip of a vast substructure of invisible dark matter clumps, each one a potential galaxy that never was. Ursa Major III Unions 1, if it is a galaxy, sits precisely at the boundary where this dark to luminous transition occurs. A dark matter halo of roughly 1 billion solar masses, containing only 16 solar masses of stars, would represent the most extreme known example of the galaxy formation process, operating just barely above the threshold of viability. It would be a system that almost did not form stars at all. A galaxy that exists only because its halo was just massive enough, just dense enough, at just the right moment in cosmic history to collect and cool a tiny wisp of primordial gas before reionization shut the process down forever. Its handful of ancient, metal-poor stars would be relics of that single, brief episode of star formation, frozen in time for more than 10 billion years, drifting through the Milky Way's halo as the oldest and faintest witnesses to the moment when dark matter first learned to make light. If, on the other hand, the system is a star cluster, the implications are different but no less important. It would mean that the luminosity function of Milky Way satellites, the statistical distribution of satellites as a function of brightness reaches a bottom defined not by dark matter halo physics, but by the survival limits of bare stellar systems in the Milky Way's tidal environment. It would mean that below a certain luminosity, the satellite population transitions from dark matter-dominated galaxies to self-gravitating stellar remnants that can mimic the appearance of galaxies without containing any dark matter at all. Separating these two populations would become a critical task for every future survey, and the tools for doing so would need to be sharpened considerably beyond their current state. Those future surveys are approaching rapidly. The Vera C. Rubin Observatory, currently being commissioned in Chile, will conduct the Legacy Survey of Space and Time, a 10-year campaign to repeatedly photograph the entire southern sky to unprecedented depth. The survey will detect individual stars at distances far exceeding the reach of any previous wide-field imaging program. Simulations predict that the Legacy Survey of Space and Time will discover dozens to hundreds of new ultra-faint satellite candidates around the Milky Way, pushing into luminosity regimes where objects like Ursa Major III Unions 1 may turn out to be common rather than exceptional. Each discovery will require spectroscopic follow-up to determine velocities, chemical compositions, and ultimately classifications. The community will face a flood of new ambiguous objects, each one demanding the same painstaking case-by-case analysis that has consumed years for the handful of systems currently known. The Euclid Space Telescope, launched by the European Space Agency in 2023, will contribute from a different angle. Its wide-field infrared imaging will map the distribution of dark matter across vast cosmic volumes through gravitational lensing, the bending of light from distant galaxies by foreground mass concentrations. While Euclid is not primarily designed to discover individual Milky Way satellites, its data will constrain the overall abundance and mass distribution of dark matter subhalos at scales relevant to the missing satellites problem, providing a statistical framework against which the observed satellite population can be compared. The numbers from simulation-based predictions give a sense of the transformation that is approaching. Current estimates suggest that the Legacy Survey of Space and Time, with its combination of depth and sky coverage, will be sensitive to ultra-faint satellites down to absolute magnitudes of roughly zero out to distances of approximately 30 to 40 kiloparsecs. An object as faint as Ursa Major III Unions 1, with its absolute magnitude near +2, would need to be closer than roughly 20 kiloparsecs to be detected even by Rubin. Beyond that distance, systems at this extreme faintness will remain below the detection threshold even for Rubin, but within that volume the survey is expected to discover a substantial new population. Simulations calibrated to the current satellite luminosity function and corrected for the sky coverage and depth limitations of existing surveys predict that the Milky Way may host between 200 and 1,000 luminous satellites. In total, depending on assumptions about the faint end of the luminosity function and the efficiency of star formation in the smallest halos, if the true number is toward the higher end, the Legacy Survey of Space and Time could discover more new ultra-faint satellites in its first few years of operation than all previous surveys combined over the past 2 decades. But discovery is only the first step. Each new candidate will require spectroscopic follow-up to measure radial velocities, identify member stars, determine velocity dispersions, and assess metallicities. This is where the bottleneck emerges. Spectroscopy of extremely faint stars, magnitudes of 22, 23, 24, and beyond, requires large aperture telescopes and hours of integration time per target. The Keck telescopes, the Magellan telescopes, the Very Large Telescope, and eventually the Extremely Large Telescope and the 30-meter telescope will share this burden. But telescope time is finite, and each ultra-faint satellite candidate requires not just one epoch of spectroscopy, but multiple epochs to identify and remove binary contamination. A single system can consume tens of hours of 10-meter class telescope time before a confident classification emerges. Multiply this by dozens or hundreds of new discoveries, and the spectroscopic follow-up campaign becomes one of the largest observational undertakings in stellar astronomy. The challenge is compounded by the lesson of Ursa Major III Unions 1 itself. Initial single-epoch spectroscopy produced a velocity dispersion that pointed strongly toward a galaxy classification. Multi-epoch follow-up reversed the picture. Any future discovery that receives only a single spectroscopic observation will carry the same risk of binary contamination and premature classification. The community will need to develop standardized protocols for multi-epoch kinematic monitoring of ultra-faint satellite candidates. A systematic, years-long campaign of repeated spectroscopic observations designed to flag binaries, stabilize dispersion measurements, and build the sample sizes needed for statistically robust conclusions. Chemical abundance analysis adds another layer. Measuring individual stellar metallicities from low-resolution spectra provides useful but limited information. The strongest classification evidence comes from high-resolution spectroscopy that can resolve individual elemental abundances, not just the overall ion content, but the ratios of alpha elements like magnesium, calcium, and titanium to iron, which trace the timescale and enrichment history of star formation. These measurements require even more telescope time and are feasible only for the brightest member stars in each system. For a system like Ursa Major III Unions 1, where the brightest members hover at faint magnitudes, high-resolution abundance analysis pushes current instrumentation to its limits. The next decade of ultra-faint satellite research will be defined not only by the pace of photometric discovery, but by the capacity of the spectroscopic infrastructure to keep up. The flood of candidates from the Legacy Survey of Space and Time will outstrip the available telescope time for detailed follow-up, forcing the community to prioritize targets, develop faster classification diagnostics, and accept that some fraction of newly discovered systems will remain in the ambiguous grey zone for years before their nature is resolved. Together, these observatories will transform the landscape of ultra-faint satellite research within the next decade. The question of how many objects like Ursa Major III Unions 1 exist around the Milky Way, and how many of them are galaxies versus star clusters, will move from theoretical speculation to observational constraint. But the transformation will also intensify the classification problem. More objects in the grey zone means more disputed cases, more ambiguous measurements, more systems where the evidence stubbornly refuses to point clearly in either direction. And this is where the deeper question finally surfaces. Not whether Ursa Major III Unions 1 is a galaxy or a star cluster, but whether the distinction itself remains coherent at these extremes. And this is played the Willman and Strader definition. A galaxy is a system whose properties require more than baryons and Newtonian gravity to explain, is operationally clean, and scientifically useful for the vast majority of astronomical objects. Apply it to the Milky Way, obviously a galaxy. Apply it to Omega Centauri, the most massive globular cluster in the Milky Way, widely regarded as a probable stripped dwarf galaxy nucleus based on its multiple stellar populations and chemical complexity. Apply it to Segway 1, a galaxy supported by both kinematic and chemical evidence. Apply it to a typical globular cluster like Messier 13, clearly a star cluster with no dark matter required. But apply it to Ursa Major III Unions 1, and the definition does not fail, but it reaches a regime where applying it becomes operationally impossible with current data. The measurements cannot distinguish between a tiny dark matter halo producing a velocity dispersion of 0.5 kilometer per second and no dark matter at all. The chemical data cannot distinguish between a single burst cluster population and an ultra-faint galaxy whose enrichment history was so brief that its metallicity spread is indistinguishable from zero. The diagnostic tools that make the definition work in brighter systems lose their resolving power at this luminosity frontier. The definition is correct in principle. It is unverifiable in practice. This is not a failure of science. It is a revelation about the universe. The universe does not draw sharp boundaries between its structures. It builds gradients. Stars shade into brown dwarfs, which shade into giant planets. Asteroids shade into dwarf planets, which shade into planets. The question of where to draw the line between these categories has fueled debate for centuries, a debate that famously stripped Pluto of its planetary status in 2006. The galaxy versus star cluster boundary is the same kind of problem, transplanted to the grandest scales of cosmic structure. Nature produces a continuous spectrum of gravitationally bound stellar systems. At the high end, the systems are unambiguously galaxies. At the low end, They are unambiguously clusters. In the middle, in the fog, there are objects that resist classification because the physical properties that distinguish galaxies from clusters become unmeasurable. What makes the fog unsettling is what it conceals. If the boundary between galaxy and star cluster is a gradient rather than a wall, then the question of how many galaxies orbit the Milky Way does not have a clean answer. The number depends on where you place the threshold, and the threshold depends on measurements that are fundamentally limited by the faintness and sparsity of the objects in question. The missing satellites problem, one of the central puzzles of modern cosmology, may not have a single solution, because the problem itself is partly definitional. Some of the missing satellites may be dark matter halos with no stars at all. Others may be systems like Ursa Major III Unions 1, hovering at the boundary, containing stars but defying classification as either galaxy or cluster. The universe builds its smallest structures in a regime where the conceptual machinery of human science begins to grind against its own limits. We want categories. Nature provides continua. We want clean distinctions. Nature provides systems where the difference between galaxy and not galaxy is smaller than our measurement uncertainties. We want to count the galaxies around the Milky Way. Nature builds objects that might or might not qualify, depending on which spectrum we observe, which binary we exclude, and which prior we impose on our statistical model. Perhaps the most important contribution of Ursa Major III Unions 1 to astronomy is not the answer it will eventually receive galaxy or star cluster, but the question it has already forced the field to confront. What does it mean for a category to break down? What does it mean when the universe produces objects that fit no existing label comfortably? And what does it mean that the difference between the smallest galaxy and the largest star cluster may hinge not on the nature of the objects themselves, but on the precision of the instruments we point at them? Return, one final time, to the object itself. 60 ancient stars, older than 10 billion years, drifting through the halo of a galaxy containing 400 billion suns. Their combined light is 11 times the luminosity of our own star. Their combined mass is 16 times the mass of our Sun. They occupy a volume of space roughly 10 light-years across, a patch of the cosmos so small and so faint that it eluded detection until a wide-field survey camera on a mountaintop in Hawaii caught the faint statistical excess of their collective presence against the crowded foreground of the Milky Way's halo. They may be sitting inside an invisible mountain of dark matter, a halo weighing roughly 1 billion solar masses, a structure so much more massive than its visible contents that the stars are barely more than decorative sparks at the center of an enormous gravitational well. In that case, they are the most extreme galaxy ever discovered, the faintest whisper of star formation the universe has ever produced, a fossil from the first billion years of cosmic history that survived tidal destruction for 10 billion years because it was cradled inside a dark matter cocoon, dense enough to resist the Milky Way's relentless gravitational pull. Or they may be clinging together through their own gravity, and the gravity of dead companions, white dwarfs, neutron stars, stellar mass black holes left behind by more massive siblings that burned out long ago. In that case, they are the faintest and most ancient star cluster ever found, a system whose survival is owed not to dark matter, but to the invisible mass of stellar corpses that share their tiny volume of space. A cluster that looks, from the outside, almost exactly like what a galaxy would look like at this extreme, and that can be distinguished from a galaxy only by measurements more precise than current technology can reliably deliver. The unsettling truth is not that astronomers found a small galaxy. It is not that they found a faint star cluster. It is that at the extreme lower boundary of structure formation, the universe stops sorting its creations into neat compartments. A handful of ancient stars may be the luminous fringe of a vast dark matter architecture, or they may be the last gravitationally coherent remnant of a stellar system slowly dissolving into the Milky Way's halo. The answer matters enormously for dark matter physics, for galaxy formation theory, for the census of cosmic structure, but the answer also depends on measurements that push against the fundamental noise floor of observational astronomy, where the signal from dark matter, if it exists, is quieter than the systematic uncertainties that surround it. Future telescopes will find more objects like this one. Some will turn out to be galaxies, others will turn out to be clusters. A few perhaps will resist classification for decades, sitting in the fog, challenging every assumption about what the universe builds at the smallest scales it bothers to illuminate. And sitting among them, roughly 33,000 light-years from where you are now, will be this one particular gathering of 60 ancient stars, still orbiting, still bound, still refusing to say whether it is the smallest galaxy the universe has ever made, or merely the ghost of a star cluster that should have dissolved billions of years ago. The boundary between galaxy and star cluster, between visible matter and dark matter, between certainty and classification, runs directly through it. And for now, the universe is not giving us a clean answer. It is giving us something more honest. It is giving us the edge of what we know, the place where the map runs out and the territory continues into darkness.